The effect of greenhouse gas emissions on our atmosphere means we have to make a lot of changes to a way of life we are very reliant on. But what are our options? Do we have substitutes? Or will industry and electricity continue with high costs to our environment? Thankfully, there are a lot of people who are working on this very challenge. Many industrial and electrical fossil fuel combustion processes are stationary or immobile. Plants like coal and natural gas-fired power plants, steel mills and cement processing plants have a chimney or a stack where all of the greenhouse gases, including carbon dioxide, are emitted. There are several processes that have been developed to capture or reduce the emissions released to the atmosphere during combustion. One of these is known as post-combustion capture, or PCC for short. PCC aims to capture the emissions that exit a plant via the chimney or stack, and then separate the CO2 by using chemical or physical sorbents to selectively remove CO2 from the gas mixture. The emissions generated in the combustion of fossil fuels are known as flue gas and generally comprise a mixture of fly ash, water vapour, carbon dioxide, nitrogen oxides and sulphur oxides, as well as other particulates. Because the fuel is combusted in air, which is around 70% nitrogen, around 2/3 of the flue gas is nitrogen. The process of CO2 separation from the flue gas stream is quite challenging. It can be an energy-intensive process and requires somewhat costly materials. Typically, in the power generation process, the fly ash, SO2 and NO2 must be removed first, as these materials can degrade the solvents that capture the CO2. Once these materials have been removed, the remaining flue gas passes through a solvent or sorbent that captures or absorbs the CO2 and later releases it in a concentrated stream. The CO2 absorption and release process is generally temperature dependent. Having the flue gas pass through the solvent at one temperature allows the CO2 to be absorbed. Then changing the temperature allows a concentrated CO2 stream to be released, to be either stored or used for some other purpose. The treated flue gas, now mainly nitrogen and water vapour, is released to the atmosphere. There are a number of projects at different scales or sizes underway that are researching a variety of chemical and physical processes for producing a concentrated CO2 stream. Because each fuel can produce slightly different flue gas compositions, the optimal absorption technology will vary across a number of combustion processes. As a process for reducing emissions of fossil fuel technologies, PCC has a number of key advantages. It can be retrofitted to existing coal and gas power plants, as well as many industrial plants, as an end-of-pipe solution, allowing emission reduction of a number of industrial processes that do not yet have zero-emission substitutes. It can also be used for partial capture and configured to treat only part of the flue gas stream. There are widespread R&D efforts underway to improve absorption technology and capture equipment that should reduce costs. Finally, the near commercial scale demonstration of PCC is underway, showing the technology readiness of this carbon capture option. There are two well-known commercial scale examples of successful application of PCC technology. The Boundary Dam PCC project has been operating at 1 million tonne CO2 capture scale since 2014, using an amine solvent process to capture CO2 from a coal-fired power plant in Saskatchewan, Canada. The Petronova PCC project has been operating at 1.4 million tonne CO2 capture since 2017, using a different but similar amine solvent process to capture CO2 from a coal-fired power plant in Texas, USA. These are large-scale coal-fired power plants making a significant impact on CO2 emissions from large-scale power generation facilities and demonstrating the potential for emission reduction of this technology. Although there are examples of operational success, there are still a number of challenges in the development and deployment of PCC. This technology has high capital cost requirements, especially in the CO2 absorption system. Operating costs are also relatively high. This is mainly associated with the replacement of and the amount of energy required for regeneration of the solvents used in the CO2 extraction process. There are also challenges in scaling up to meet the size requirements of large-scale operations. Some PCC technologies are currently available at only relatively small scale. The amount of space required to retrofit a PCC facility is also significant, as many older power stations simply don't have all the required room to easily add carbon capture capability. Despite allowing for improved environmental conditions by reducing emissions, PCC also has some environmental challenges. These refer mainly to reducing its high water usage and controlling of emissions, as this technology is not yet capable of capturing 100% of CO2. Another key challenge is associated with the wide range of PCC options that are available or currently being tested. Too great a selection means there is a risk of dilution of effort. In other words, there may be too much choice and not enough money to drive the right PCC technology to the required maturity and scale. There may also be insufficient time available to take a standalone, immature technology to technical and commercial maturity in the 2030 to 2035 timeframe. Taking a PCC technology from concept to commercialisation can be expected to take 10 to 15 years, even on an aggressive, well-funded schedule. Individual demonstration projects typically require approximately 10 years from inception to operational proving, which includes approximately 5 elapsed years to undertake the works from final investment decision to operation. The demonstration of technical and commercial readiness of PCC technologies in full chain, including capture, transport and storage, is crucial to confirm maturity to stakeholders before wide-scale deployment can occur. Along with the challenges in carbon capture at the source, full-scale PCC projects will need a sink for CO2, such as deep geological storage, enhanced oil recovery, or some other long-term storage solution. This may be the main decisive factor for whether or not carbon capture is a possibility for many fossil fuel emitters. This technology can provide significant emission reduction while allowing the continuance of our industrial and electricity sectors on which we so heavily rely. If the deployment of this technology is to occur in time to meet those required emissions reductions, we need to be working hard to overcome the challenges within this promising technology solution.